All right, infinite limits, let's go. Let's take a look at two limits. Let's see what happens. I think we understand, you guys can tell me something about this limit right away. Does that limit exist? Why not? Zero in the denominator, you can't cancel that factor top and bottom, right? Well, let's do something more. Let's see what's happening. Is there an open circle or an asymptote? We know it's an asymptote, right? Why? Because we can't cancel a factor top and bottom. That's great. That's cool. We see it right away. Well, let's do a little bit more and see where it's going as we approach 2 from the left. Let's see what's happening to the function as we approach 2 from the left. Let's see here. Okay, approaching 2 from the left means we're plugging in or substituting in like 1.999999, correct? If we plug in that number is approaching 2 from the left, what happens down here again? Just in the denominator, not the whole thing yet, just in the denominator. Small, positive or negative? Negative. So if we plug in like 1.999999, we're gonna get like negative 0.000001, right? Okay, what's 3 divided by negative really small number? Negative infinity. Okay. So that's a descriptor of what's happening as you're approaching 2 from the left. 1, 2, we're approaching 2 from the left, and we're going to go off to negative infinity, right? Okay, obviously it's going to look a little bit different than this. I'm just drawing a quick sketch. Okay, now what's happening as we go towards 2 from the right, approach 2 from the right? That means we're substituting in numbers just a little bit bigger than 2, so 2.00000001, right? If I subtract 2 from that, I get 0.00000001, however many zeros I said, obviously, right? What's 2 divided by really small positive number? Positive infinity, okay? So we can tell, or we know that we're doing that as we approach 2 from the right. And we all know that there's going to be an asymptote here, right? But it seems to me like something formal is coming up that we're going to use to define why there is an asymptote here, or a definition of a vertical asymptote. And guess what? It has to deal with limits. Okay? Well, what about these two? Do we have a discontinuity at x equals 3? Is there a discontinuity? Yeah? Okay. Is it a hole in the graph or an asymptote? Asymptote, because you can't cancel both factors of x minus 3, correct? Okay. Is that asymptote a removable or non-removable discontinuity? Non-removable? Yep. Okay. Well, let's see what's happening as we approach 3 from the left and right. Limit as x goes to 3 from the left. I'm just going to put f of x right now. Okay, let's approach 3 from the left. That would be number smaller than 3. That would be 2.99999, right? 2.99999 minus 3 would be negative 0.000001. Now square that number. Now what happens if you square a number less than 1? It becomes smaller, right? Between 0 and 1. Or I should say between negative 1 and positive 1. If you have a number between that range, you get square it. My goodness, tongue twister. Square a number less than 1, positive or negative, then it becomes a smaller number. Well, for instance, 1/2, square 1/2 is 1/4. Okay? So what's the result then? Positive down here, 2 divided by a positive small number, positive infinity. Okay, and limit as x goes to 3 from the right. Number is bigger than 3, 3.0001 minus 3, that'd be a positive 0.00001. Square that number. It's a positive small number still, right? So 2 divided by a positive small number, infinity. So this would be a case where at 3, 1, 2, 3, we approach infinity as we get closer to 3, and similarly on the other side. Does the limit exist at x equals 3? I would say no, right? But some people, like we've said, remember, if they both go towards infinity, some people might say infinity for the limit in general. But it is definitely okay to talk about the descriptors of the left and right hand limits. Okay, the limit does not exist. Some might say unbounded behavior. We've talked about that before. Definite discontinuity, and it's a non-removable discontinuity because we have an asymptote. Okay, and how about the bottom one then? What's the limit as x goes to, what do we use this time? -2 from the left. I'm going to use f of x, that's the name of the function. And then while we're at it, I'm just going to write out the other one. As x goes to -2 from the right of f of x. Okie dokie. Plugging in a value to the left of -2, -2.00001. Add 2 to that, that'd be -0.00001. Square that number. Creates a positive small number in the denominator. -3 divided by a positive really small number, negative infinity. And remember, I'm just picking one random value. The limit makes us go closer and closer and closer, show a tendency. Okay. How about -2 from the right? What's going to happen down here again? Positive really small number. -3 divided by a positive square number. Infinity. Okay. So similarly, we looked at both one-sided limits approaching negative infinity. Now, how did we get both one-sided limits pointing in the same direction when back here they did not point in the same direction? Squared what? The denominator factor, yep. What if there was a power of 3 down here? Would they be both in the same direction or opposite directions? I'd say opposite, because if you cube a negative number, that's a negative number, right? So I think it depends on the power, right? So this is how we can bend these one-sided limits to be both in the same direction. Okay? Questions on that? Yeah. This is just a quick sketch. Just a quick visual representation showing that as you go towards -2, you're going to a negative infinity. Yeah. In chapter 3, I'll be on your case about drawing these pretty accurate. So that takes us to the meat and potatoes of this lesson, the definition of the vertical asymptote. If x approaches infinity or negative infinity as x approaches some value of c from the left or from the right, then the line x equals c is a vertical asymptote of the graph of f. So what does that mean? If the limit as x approaches c from the left or from the right, and I could put left or right. I could put minus plus or plus minus right here. I'll just write it again. Now this is a big OR statement, guys. They don't both have to be true. As long as we approach infinity as x approaches a number from the left or from the right, doesn't matter, that we have an asymptote, vertical asymptote. Or Mr. Molly, when we have just approaching infinity from the left or from the right, when would that happen? Well, piecewise function where the domain is broken up, or maybe like a log function that approaches the asymptote from one side. How would they ask a question like this, or have a question where you have to have this type of knowledge? They might say, there is a vertical asymptote at x equals 5. Which of the following are true? They might have like the limit as x goes to 5 from the left, f of x equals infinity. They might have the limit as x goes to infinity, f of x equals 5. You have to pick the right one. Okay? So we looked at all these different times when we have a vertical asymptote back here. And we knew they were vertical asymptotes, but now let's add a little bit of formality to this, and we can define we have the definition of a vertical asymptote now because we have limits. Pop quiz. Can you cross a vertical asymptote? Okay. Can you cross a horizontal asymptote? I don't know. Okay, we done? We good? All right. Define all vertical asymptotes of the graph of each function. Letter A. Do we have a vertical asymptote for A? Do you agree? Yeah? Where at? Okay. So we could say vertical asymptote. Vertical asymptote at x equals -1. Okay. What if I made you guys justify or give a reason for your answer? We could say because, and then, well, how is a vertical asymptote defined? By a limit. So now we have to have a limit as part of our justification. The limit as x goes to -1. I'm going to say from the left, I'm going to put f of x here. That's legal. You can put f of x, or you can put the whole fraction. I don't know why my negative sign is there. I'll just elongate it. There we go. That just looks weird. Okay, what would that be? Positive or negative infinity? Negative infinity? You think so? Yes? Okay, -1 from the left, that'd be like -1.00001, and that would leave you -0.00001 times 2. Well, it's still gonna be a small number. 1 divided by a really small negative number would be negative infinity. Mr. Bonley, do I have to have the other one? -1 from the right? No, you just have to have one of them. That's it. You could have both. That's fine. But you only have to have one. Pop quiz. Would -1 from the right be negative infinity? Or to be positive infinity? be positive infinity. Yeah. If this was squared, then what? They'd be both up, wouldn't they? Okay. All right, good. No need to justify for these two. Let's find the vertical asymptotes. Yeah.
Is there a way to tell when the function goes to infinity or negative infinity without putting in values?
Just thinking it like I was doing. That's the quickest way, I think. Yeah. But back here, right here, okay, it doesn't matter what's in here. You're squaring it, right? So what's the denominator going to be? Always positive, right? Always, always, always. So positive divided by positive, so that's going to be positive infinity. Positive divided by, or negative divided by positive. So that's how I would think about it. All right, what about this one? Okay, I think this deserves a factoring. Denominator, that factors, that's difference of squares. X minus 1, x plus 1. What's the factor pattern for sum of squares? Is there one? No, there's not one. You can't factor that. Sum of cubes, yes. Sum of squares, no. All right, do we have any factors in the denominator canceling factors in the numerator? I don't think so. That means we have vertical asymptotes at x equals 1 and x equals negative 1. Okay? I'm not going to make you guys put the justification for these right now. I just want to do it once so we know how to do it in the future if we need to. Remember, when you justify, go back and look at the definitions and the theorems and the postulates. Pop quiz. What are the discontinuities for part B? Yeah, what part of the three-part definition adds justification to your answer? Go before that.
Nothing there.
Be more academic, please, in that answer.
At f of 1, it's undefined, and at f of negative 1, it's undefined.
What's it?
The function.
Okay, you could say f of 1 is undefined, f negative 1 is undefined. You can say f is undefined at x equals 1 or x equals negative 1. Okay, cool. So if it fails the first part, just state that. Yes, I agree, the limits do not exist at negative 1 and 1, but you could just define by the first part. How about cotangent? Everybody's favorite. What is it? What is cotangent? 1 over tangent. Okay, change that. Make it different. What I say? What I say to do with cotangent and some of those other functions? If you don't know how to figure them out.
Change them into sine over cosine.
Sines and cosines. Change everything to sines and cosines because that's the x's and y's on the coordinate plane, right? Okay, but cotangent is not sine over cosine. Cosine over sine. So now to figure out where cotangent has asymptotes, we have to know where sine is 0, right? Okay, so when is sine 0? At 0. When else? When else? What else? What else? Okay, and keep going, right? So sine is over here, that's 0. Sine's the height is 0 here. Back over here, height is 0. Back to beginning, height is 0. And then the wrapping function or the trig values, you keep going around that unit circle, right? What if we go backwards? Negative pi, would that make 0? Yep. So to count for all of these, you could say x equals pi n. That takes care of all the multiples of pi. That's what it is, multiple of pi. But then you have to make sure n is an integer. What number or letter do we use for integers? You guys remember that? Z, actually, integers. That was a long time ago. That was algebra 1. Or you can say n is an integer.
Wait, what is the thing next to the n?
What does that mean?
What is that?
It's an element. It means element.
So you're right, n easy. Oh.
Or you could say, or you could write it out. N is an integer. Okay. Okay. Here you go. Use the quickness. All right, that'd be x and x, factors of -8. So one's positive, one's negative. Probably 4 and 2, right? Bottom one's easy. Okay, x minus 2, that factor cancels. So where is our vertical asymptote? So vertical asymptote at x equals -2, that's where it would be at. That's the equation of that vertical line, right? What about x equals -4? That's a vertical asymptote too, isn't it? I'd say no. What is it though? 0, the function, because it makes the numerator 0, right? Okay, how about x equals 2? What is x equals 2? Hole in the graph. Is that discontinuity if it's a hole in the graph?
Yes.
What type? Cool. Is there a discontinuity x equals -2? What type? Non-removable. All right. Now what about as x goes to positive or negative infinity? Now again, I've kind of already showed you guys most of this. So let's draw real quickly the limit as x goes to infinity of some function f goes to infinity. What would that look like again? As you go to infinity, what happens? Like that? Something like that? Could it be like this, so it doesn't get steeper, it gets shallower? As x goes to infinity, is y going to infinity? It could look like that too. That's be chapter 2 and 3, concavity, concave up, concave down. Okay. What about as x goes to negative infinity? What's happening for the function f if the heights go to infinity? Like that. And it could look like that too. Okay, we've looked at that. Pop quiz. Does this limit exist? Does the limit as x goes to infinity f of x, if that result is infinity, does the limit exist? No, why not? It's not a what? It's not a number. What's the other thing I called it? Or what kind of behavior is this? Unbounded behavior. Okay. All right, what about if x goes to infinity? If we have the limit as x goes to infinity for some function f, let's say you approach 2 though. As x goes to infinity, you're approaching 2. Could it be like that? Yeah, sorry, my apologies. How about, I'm looking at it sideways a little bit. How about like that? Could it be like that? What does that represent then? Horizontal asymptote. Yeah, actually this would be a horizontal asymptote. I'm showing it to you now, but we will define that later. This is the definition. If x goes to infinity and y goes to a number, then we have a horizontal asymptote, which we'll define in section 3.5, I believe, if I remember correctly. Okay? Here's something to think about. Here's something to ponder about when you're on a bus ride for sports and you don't know what to think about because you've looked through all of your snaps and your TikToks and your Twitter and everything else you look at except for texting. Can a function go above that horizontal asymptote and then approach it from the top? Could that happen?
It's impossible. Because that means unless they go, they go through to it can only get closer.
What's up?
Could it have a hole in the graph where it crosses the asymptote?
It could. Does it have to? Can you?
Asymptote, do you like restrict?
I don't know. Could that happen?
Restricted asymptote. Yeah.
I don't know. What do you guys think? Can it cross a horizontal asymptote?
Only for someone who anything can happen. I think it's possible. But
So you're saying there's a chance?
not in this one.
Not in this one? Okay.
Because there's not a hole in the graph. Unless
Well, are you guys confusing domain with what's happening as we go towards infinity? Is this a function?
yes.
If we go towards 2 at infinity, we have a horizontal asymptote. Does it say you can't cross the asymptote? I think you can do this. In fact, I know you can. All right, moving along for the essence of time. This is going to be later also, but let's go over it now. Why not? Okay, limit as x goes to infinity. Okay, of 2x squared over x squared. Think about this, guys. Plug in a big number on top, big number on bottom. Plug in a bigger number, and even a bigger number. What's going to happen here? What is this number going to approach? What are we going to approach here? Why 2? Yeah, you could cancel x squareds out, right? And then the limit of a constant's the constant, right? Okay, good. But what about this, smarty pants? 2x squared plus 1 over x squared plus 3. Now do some canceling. Well, guys, as we go to infinity, does plus 1 really matter? If I have $1 billion, does $1 really matter? Not necessarily. To some it might. Yeah, $1 billion though. If you go to infinity, does adding 3 really matter? So that would basically make this plus 1, this plus 3 insignificant, and you're back to square one again. Okay? So if the powers are the same, top and bottom, it's just a ratio of the coefficients. And don't worry, we're going to go over that later. What if we go to infinity and we have a cubic on top and a squared on bottom? Why infinity? Yep, it's going to grow faster than the bottom, so we're going to infinity. And you could cancel these x squareds with 2 of those. You'd have 2x, right? 2 times infinity. What's that going to be? Infinity. What if the power in the bottom is bigger than the power on top? What are we going to go towards? So you take a number divided by a very big number. 0. Okay, so this would be same powers. Top heavy always goes to infinity. Bottom heavy always goes to 0. And we'll talk about some others later. I just wanted to go over those real quick. Okay? All right, this is from Fun to Know stuff. We kind of know what's going on. We're preempting some things to get you guys a whole handle on limits.